Okay, guys. So we will be discussing and starting theory of failures. This is, as we have discussed, the last part of static portion of the structures. So I'll give you a brief background and then we will talk about the theories. It is kind of a very straightforward topic, but very, very relevant related to GATE 2025. Also, they have asked a question. Initially, from 2007 till I can say 2018 or something, they were not focusing more on theory of failures, but then they have started asking question every year on theory of failures. It's a beautiful concept, very much important when it comes to reality. When you start working in industry, this is the thing which you will be using in every day-to-day activity. Without theory of failures, you cannot design any component, and specifically aircraft components. So let's discuss what is the cyclic process and how this theory of failures is helpful and what we will going to study in today's lecture. So it works something like this. Okay. So let's say you want to design any component. Let's talk about you want to design an aircraft wing. All right. Let's say per se you want to design an aircraft wing. All right. So this is how the aircraft wing will look like. And then you have the other portion. So let's say as a designer, your motive is to design this aircraft wing. And various people will have various, I can say, parameters. So maybe one person is saying length of the wing or span of the wing should be maybe 2 meters. Another one is saying 3 meters, or maybe depending upon the thickness or maybe the material used. Many people will give different criterias. All right. So let's say we have different criterias, but in the end, I want my aircraft to fly, carry the load, do all the maneuvers, and keep people safe. That's what the whole intent is of designing the aircraft wing. So what you people do first as an engineer is you take your structure, whichever you want to design, and analyze what kind of loads will act on this. So you people know on this, there will be a lift acting upwards, there will be weight acting downwards, there will be what is known as bound vertex, which will help us to generate lift. You will learn this in aerodynamics, what are bound vertex. There will be wingtip vortices, which is coming from bottom portion to top portion because of high pressure to low pressure motion. You know these things, it's okay. If not, it's perfectly fine. So you have various kind of loads acting on this. The intention is that, let's say, I'm just complicating this. Let's say there is some kind of torque also applied here. So when something like this happens, so you analyze all the loads, and now if you people see, because of torque, there will be a shear stress. Because of this lift and weight, because this is fixed here, it's kind of a cantilever beam, there will be a normal stress. Because of this movement, there will be a normal stress. Because of these movements, there will be torsion. So there are multiple stresses coming. So as an engineer, your task is not that straightforward because you have n number of loads acting on the system you want to design, and each kind of load will give you a particular kind of stress, either a shear stress or a normal stress. So it is very, I can say, tedious, or it is very tricky which stress to consider, which to neglect, or how to consider all of them together. So what people thought that if you have any stress body and you have multiple stresses acting on this body, what we're going to do is we're going to transform these stresses into what is known as principal stresses. And we have spent enough time and detail in basic elasticity in calculating principal stresses. So whatever, if you have some sigma x, you have some sigma y, or maybe sigma z or tau x, y, any kind of stresses what you have, you can combine all those stresses into what are known as principal stresses. And if you recall your basic elasticity, it is sigma 1, it is sigma 2, and if it is 3D body, it is sigma 3. Keep this in mind. These are the real stresses acting on the system. So maybe some stresses are coming because of bending, some are coming because of torsion. And as a designer, for your easiness, you have converted them into some meaningful numbers which you people can interpret better and you are naming those stresses as principal stresses. Now, so this complete structure is converted into these stresses, and these stresses is converted into principal stresses. Now we will take these principal stresses and go to theory of failures. So theory of failures will only and only work with principal stresses. You will not talk anything about bending stress or torsional shear stress or shear flow. These blah blah things, theory of failures don't bother. Theory of failure says whatever you have, please first convert them into meaningful numbers, which are principal stresses, and then use these principal stresses and design your system. Now, what do you mean by theory of failures and design of systems? You have your principal stresses ready. Now, typically, as per our Gates syllabus and as per all the standard textbooks, if you open, right, you will find 5 theories of failure. So there are different scientists who propose different theories. I'll give you a gist what this means. So one scientist came and say that if your stress is the largest stress is more than the stress which material can handle, that makes sense, right? If your material can handle only 100 MPa, this is your material stress, and your system is producing 200 MPa, then even a child can say that there will be a failure, right? We will see this is known as Rankin theory of failure. Don't write anything, I'll give you in sequence properly. Another scientist came and say, it is not that simple. You should not directly look into your maximum stress and the material maximum stress. Another person came and say, please look into maximum strains. If your strains are more than maximum material strains, then there is a failure. So different scientists have different theories. Another person came and say, don't see normal stresses, see maximum shear stresses. When your maximum shear stresses go above the material maximum shear stress, there will be a failure. Now, there is a possibility that you people are not getting the words I am saying now, but when we start developing these theories, right, I will explain each and every point in detail. What do you mean by shear stress, material shear stress, and so on? What I'm trying to convey is from our first year of engineering, and even till now, and even till my last lecture, it is always being spoken that if your stresses are more than material stresses, there will be a failure. But scientists have different theory. They say stresses are not the only thing which matters. Sometimes energy matters. If your distortion energy is more than the material distortion energy, there will be a failure. So stresses definitely give us an idea, but there are different ways of looking into those stresses and comparing with the material properties. So now our task for today is, what are these 5 theories? So we will be discussing this, and please take this as a summary. This lecture, your motive is, and once I'll close this lecture, you should be confident in all of these. First, what are the names? Because in your exams, they will use this theory. So you should be very clear with the naming convention. All theories have different names given to it. So this we will see. When I start a theory, I will give you the name properly. Then, what is the equation of that particular theory? So we will see what is known as criteria, theory of failure criteria. Then we should also look into when this theory is applicable. So all the theories are not applicable for all materials. There is one question, I think in 2023 or 2024 somewhere. We will see when we start gate numericals. But when you can apply this theory properly without any errors. And then fourth, what will be the corresponding diagram for this theory? So every theory will have a diagram. This is asked in 2024. And I think some 3-4 times they are continuously repeating, tell the this diagram corresponds to which theory and so on. We will see, and you will be clear. So once I'm done with all the theories, right? All the five theories, you should know all these things. You should know the name. You should know the equation, or I can say criteria. You should know when you can use this equation properly and what is the corresponding diagram. And you know, all these theories will only and only work with principal stresses. So all the equations I'm going to develop, you will find these terms sigma 1, sigma 2, and sigma 3. How these sigma 1, sigma 2, and sigma 3 are calculated, you have to revise your basic elasticity. Any stress element, when you know all these stresses, you can easily evaluate your principal stresses. So basically, when a theory of failure question comes in your gate exam, it's kind of combination numerical of basic elasticity plus theory of failures most of the times. Now, starting with the theory, please give me a quick nod if I'm clear up till now. What is our task today? What we're going to understand? What this topic of theory of failure means? If it is clear, then we will move ahead. Clear? Okay, perfect. So let's go to first theory. Now, this theory is known as, and this is the naming convention. So this is the first theory we are talking about. The first theory name is maximum shear stress theory. This is one name, and this is very common name. In your exams, they can specify this name. The other most common name for this theory is Tresca theory. I'm 1000% sure in your exam, they can use any of these two words. But for completion, this theory is also known as stress difference theory or Guest's theory. These are nothing but the name of the scientist. But I insist you people to remember these two names, maximum shear stress theory and Tresca theory. These are one and the same thing. They will use these words in your exam. So first question, first thing, the name. Second, Tresca theory is widely accepted when it goes for ductile materials. Now there are two kind of materials. If you people don't know, let me give you a brief introduction here. You have ductile, and the other kind of material you have are brittle materials. Now the property of ductile and brittle materials is very simple. Brittle material, example, glass, when you apply a load to it, there is a direct fracture. So if you see any stress versus strain plot, I have discussed this in basic elasticity. Let me quickly revise it. So when stress increases, strain increases, it's a linear, and then suddenly you have a fracture. So no complicate things in brittle materials. You know, when you apply load to a glass will eventually break into pieces. That's what is known as fracture. So no fishy things, very simple, straightforward material. But when it comes to ductile materials, right? I hope you people recall your basic elasticity lecture when we have discussed. So there is a linear portion, then there is a non-linear, then there is a yield stress, which we name it as sigma y. And after this, you have some behavior like this. Now, this zone is basic your plasticity zone, and this is nothing but your elastic zone. Now, what is plasticity? Plasticity is if you reach this zone, you will not going to regain your original position. And typical engineering materials like steel, aluminium, copper, brass, iron, all these are ductile materials. I'll give you a simple example. If you have a bar and you apply some load to it, this bar will elongate. Correct? It elongates to certain extent, and then you leave it. When you leave it, it comes back to its initial position. That means this is an elastic zone. But if you apply more load, let's say you stretched it this much, and when you leave it, let's say it came only till this point. So this bar becomes something like this. So this original shape is being permanently changed because of plastic deformations. So this is a failure, right? So ductile materials will work with this stress. We will say anything after this, there is a failure. Ductile material failure works with yield stress. Don't worry, I'm just giving you this verbal explanation. I will write each and everything when we'll start the theory. Whereas brittle materials works with ultimate stress. Ultimate stress means at which there is absolutely a fracture. The body is broken down into two pieces. That's the major difference between ductile materials and brittle materials. Now, you people know all our engineering metals are typically ductile. I know we will use glass and all these things, but these are not typical our engineering materials, right? Engineering materials are aluminium, steel, copper, zinc, cast iron. All these are typical engineering materials and all are ductile materials. This is the reason Trisca is a most widely used. I should not say most. Von Mises is actually the most, but Trisca is a theory which is used only and only for ductile materials. All right, first statement. So if you see, I have given you the name and I have told you when it is applicable. It doesn't mean that you cannot apply Trisca for brittle materials. You can apply, but it will give you some wrong answers. It will not give you good answers. So no one can stop you, but it is not recommended to use Trisca theory of failures for brittle materials, and it gives you good answers for ductile materials. All right. Now, what this theory says? This theory says if the shear stress exceeds, let me write it. If the maximum shear stress, maximum shear stress of your design, what you're designing, exceeds the tensile yield stress, the failure will happen. Now, I know this is somewhat tricky. This is the reason I never like theory statements for understanding any concept. Let me give you an equation and then I'll explain you this in detail. Now, before going into that, can you people tell me if you know your principal stresses? You know your principal stresses are sigma 1, sigma 2, and sigma 3. I just need a thumbs up, a yes or no. Do you people recall do you people recall from basic elasticity, if you know your principal stresses, how we can calculate maximum shear stress? Any idea? Any reminder? If you know your principal stresses, it was sigma 1 minus sigma 2 divided by 2, right? So if you know sigma 1, if you know sigma 2, sigma 1 minus sigma 2 divided by 2 is nothing but your maximum shear stress, correct? Now, maximum shear stress of the system. So please listen to this. You have sigma 1, sigma 2 divided by 2. This is one maximum shear stress. But I'm talking about 3D. If it is 2D, then this is your principal stress. This is your maximum shear stress. You have to take all possible combinations. So sigma 2 minus sigma 3 divided by 2, sigma 3 minus sigma 1 divided by 2. And out of all these three, you take the bigger one. So if you know your principal stresses, you calculate your maximum shear stress and take the biggest one of them. If your maximum shear stress is less than or equals to the material yield shear stress, then you have a safe design. If your value is more than the material shear yield stress, and this is a material property, they will give you this in the exam. There is no numerical or formula to calculate it. Every material has their own tensile strength, shear strength. So this will be always and always provided to you in the numerical because this is a material property. All these are experimental values. Every material steel has a fixed value of sigma y, tau y, and so on. So if your stress is less than the material property, you have a safe design. If your stress is more than the material property, your design will fail as per Tresca. So if you see, Tresca is not directly comparing your normal stresses. Tresca is not saying if your sigma 1 is greater than sigma y, there is a failure. No. Tresca says you first calculate your maximum shear stress. And if your maximum shear stress is more than the material maximum shear stress, you will definitely get a failure. So I have given you an equation, and this is very simple equation to remember also because we have done basic elasticity. Now comes the most tricky part, which ideally speaking, if you go in standard textbooks, right? In textbooks also this derivation is not provided. If you go to any lecture, right, any YouTube video or anywhere you find this lecture, hardly you will find going to find these derivations. But when you join your MTech, right, and you started advanced elasticity, and when you go into the lab also, you will find these derivations starting on your first or second or third day only. From there only, I'm giving you this derivation. Even I have skipped this in your study material books. Now, what I'm saying is this. Anything I'm going to block, you will going to by heart. So this is the formula we should remember. Now, what they will do in your exams is they will give you sigma y rather than tau y. You need to understand the difference. This is tensile yield stress. So if you apply a tensile load, what is the maximum stress your material must be greater than tau y for failure? Yes, yes. So what I have written is this equation is giving you a safe design Vedika. If your left hand side, just understand in this way. These are your stresses and this is material property. If your stresses are more than the material property, there will be a failure, right? Agreed, Vedika? Now, this tensile stress tells you if you apply load in the normal direction, what is the maximum stress your material can hold. Similarly, tau y, again, this is shear yield stress. So if you apply a shear load, what is the maximum shear stress your material can hold is what is known as tau y. And you people can agree both are different thing, right? One is the material property in shear direction and another one is the material property in the normal direction. But both are material properties and it is same material, right? No, 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 Purnish. You have to, any one of them will be the largest, right? You have to take the max one. Clear? Okay. Now, whatever I'm going to write now, you people will not do this derivation, but that will help you. I will derive only in this theory, and later I will give you the ratios, which will make sense. So please listen to this, what I'm going to do now. I'm going to take, let's say, a bar, and to this bar, I'm going to apply normal material normal stresses. So this is my test specimen in my lab. And to that, I am applying a load at which this material will fail. So there will be a failure in this material. That's what we are trying to do. Is this clear for everyone? Guys, are we okay? Clear? All right. Now, Sai, I'll come to this. Sai, just tell me one thing. I'm saying max of it should be less. If max of it is less, the other two are always less, right? If one is 20, one is 30, and one is 100, if 100 is less than tau y, then 20 and 30 is automatically less, right? So don't take these three values. Just take the bigger one, max, and then compare it with tau y. Okay. Now, guys, please listen to me carefully. This is a specimen I have taken in my lab, and to it I have applied yield stress so that there is a failure. Now, I want you people to tell me this. What is what are the principal stresses in this case? Can I say my principal stress, which is major principal stress, is equals to sigma y? The sigma y is yield stress. There is absolutely no stress in y direction, and there is absolutely no stress in z direction. Before going further, do you people agree on this? This is a pure tension test. This is your first semester IIT lab in which you will be testing steel specimens. So you took and you got your three principal stresses. So Punesh, I have given you a bar and you have applied a normal load to it. Can I say there will be one stress in this direction, which is nothing but sigma y? This stress, there is no stress in this direction, right? And these are principal stresses because there are no shear stresses. Agreed, Punesh? What are principal stresses? Principal stresses are stresses when there are no shear stresses. There are no shear stresses. So whatever stresses I have are my principal stresses. And because it is pure tension test, I have stress only in one direction. So I've written sigma 1 equals to this. Don't think this is y. This is not y direction. This is yield. Let me write it so that there is no confusion. And there is no stress in y direction, no stress in z direction. So I have these stresses. Now, if you have done your tension test, you got these three stresses. This you can easily do in your lab. It will take maybe 2 or 3 minutes and you will get your answers. Then for this, I will calculate my tau. And tau is nothing but sigma 1 minus sigma 2 divided by 2. Sigma 2 minus sigma 3 divided by 2. I'm applying all these three formulas. So if you people agree, out of all these three combinations, what you're going to get will be sigma y by 2. Just tell me yes or no. Do you people agree on this? If you take your sigma 1, sigma 2, and sigma 3 and apply your theory, you will going to get this, which is equals to tau y, right? See what I have done? Tau y, I have copied it here. And when you apply this, you get this equation. So what this equation is telling you, please listen to me very carefully, and that's what I'm saying. Anything I'm going to block, you should buy hard that thing. And you will find this in all textbooks. You will find for maximum shear stress theory, only for maximum shear stress, which is also known as Tresca, tau y by sigma y is basically 0.5. No one in the world can change this ratio. Now, why we have done this? Most of the times in your gate numerical, they will give you Tresca theory to apply, and they will give you sigma y. But we have learned this formula, right? If our shear stress is less than the shear stress of the material, then our design is safe. So we need something to convert this sigma y into tau y. Or if you people agree, I can write this tau y as sigma y by 2 also, right? And I will solve my numerical. Do you understand why this thing is derived? Because when you do a tension test, you don't need to do your torsion test also to get separately what is tau y. You have done your tension test. You got your principal stresses, you have applied your theory, you got a relation. Now, if in the exams they give me tau y, I will directly substitute the tau y here. If they give me sigma y, I will take sigma y divided by 2, calculate my tau y, and then substitute it here. So I will never ever going to miss a numerical, whether they give me tau y or whether they give me sigma y. This is the reason when I have used the word, I'll give you equations. So every theory, you will learn one formula and you will learn one ratio. Rest all, whatever I have written is garbage. I'm not removing this because if some people are writing it, you can write it. But keep this in mind from next theories, I will give you the name, I will give you the equation, I will give you the ratio, and then last is the diagram. Now, before going further, okay, let me finish that diagram also, then we will discuss all the doubts together. So, the diagram for theory of failures for Tresca is basically a hexagon. Let me write it that here. Let me explain this because this is ours in 2024 itself. Now, how the diagram looks like. So, what we will going to do is we will going to draw. Let me showcase this and then I'll explain you. All right, this looks like a hexagon. You have 6 sides in this. Now, what these sides replicates? This side, this says this is your boundary. So whether you are in X direction, Y direction, anywhere, your maximum stress you can go is sigma Y. And similarly, this is also sigma Y. So what we are trying to do is, and similarly, this is minus sigma Y, and this is minus sigma Y. So what you have done on all these directions, you have created a boundary for you. And now what we have done simply is we have connected these boundaries. You see, we have connected this, we have connected this, and then we have connected this with both the regions. Now, please listen to me, and this is very simple. Tresca says anything inside this region. I'll give you a very simple example. Hopefully, then it looks easy for you. It is basically sigma 1 and sigma 2, yes. Let's say, let's say this is sigma 1 is 100 and sigma 2 is 50. Let's take an example. Or maybe sigma 3 is 50, whichever one is bigger. And let's say my sigma yield was 200. So then definitely this is also 200, right? Then this is also minus 200. And this is also minus 200. If your stresses are 150, you will lie somewhere here, right? 100 will be here and 50 will be here. So you are here. You are inside this hexagon. That means this design, which I have marked in black dot, is a pass. You don't have to apply any of these theories, equations, and blah, blah. That's what Tresca has done. He has generated a envelope depending upon the material property. And then you need not to apply any equation. If your body is inside, you are pass. If your body is outside, you are failure. Now, let's take an example. If your stresses are, let's say, 300 and your sigma 2 is minus 20. See where it is? Sigma 1 is 300. So you are here, here, and minus 20 here. So definitely you people can see this is a fail, right? Let's take an example. Sigma 1 is minus 200 and sigma 2 is, let's say, 10. Think about this. Sigma 1 is minus 200. So I reached here and then plus 10. I will be somewhat here, fail. And I can give you infinite number of examples of pass and fail. So Tresca says, this is my equation. If you plot it, it will look like a hexagon and you will be absolutely safe And guys, again, this 200 was just an example. Please don't think it's an absolute value. All right. So it totally depends upon the material. I have just simply given material property as 200, but it can be anything. If you are inside this zone, your material is safe. If you are outside this zone, your material will fail. Inside the zone means this condition will also be satisfied. Outside the zone means this condition will be a failure. So in our first theory, we have learned the name, we have learned the equation, both the equation and the ratio. We have learned that it is only applicable for ductile materials, and we have seen that its diagram is looks like a hexagon. This is our first theory of failure. Open for doubts. Anything you want me to repeat, any clarification, tell me. Otherwise, we'll move to second theory, guys. Okay, let's see. Doubts. Okay. So first thing is, I'll tell you one simple thing here. Uh, Punesh asked why hexagon, sir. So one thing from the theory, and you will understand this more detail in deep in the next theory. If you see your equation has all the powers of one, meaning I'm saying this is tau to the power one. Even your sigma one and sigma two is to the power one here. And one means linear. Linear means straight lines. Correct? Then what we have done, we know if our stresses are more than yield stresses. So you see, we have generated the envelope of sigma y, sigma y, sigma y, sigma y. And then we have combined or joined them with the help of a straight line. You will see when it is square, how the graph will convert into a different shape. Is this clear, Punesh? Okay, perfect. Next. So can you explain the essence of sigma y by 2 again, and hope it's for uniaxial stress only, and can we relate T in hexagon? And can we relate T in hexagon? I understood your first part, Akash. I can explain that, but and I hope it is for uniaxial. Can we relate T, tau in hexagon? Tau is already related, right? This is sigma, tau is sigma y by 2. This is the reason you have sigma y twice on both the sides. This is your best envelope, right? You have created twice of the width. Correct, right, Akash? If you see in the hexagon, it is already related, right? And second, essence is this. The only essence is, see, I'll give you steel. Let's say in your exam, I'll give you the material used is steel, and steel has sigma y equals to 200 MPa. This is the numerical I have framed. All right. You know your Tresca theory is this. Is it not that for solving Tresca theory you need tau y? Akash, yes or no? You need, right? Then you need a conversion, right? So for that conversion, you have already done a lab test, and this is universal. No matter what kind of, it is a material property, right? So you can use tension test, even if you do a torsion test or if you do a hammer test, any kind of test, it will give you same relation because it's a material property. So this relation helps us to convert this sigma y into tau y, and I will use in this numerical as 100 MPa. Because this is 200, I will use this relation to calculate this as 100 MPa. Perfect. This is clear. Let me go to next. Sir, what if sigma 1 and sigma 2 both are 0? If sigma 1 and sigma 2 are 0, then sigma 3 will be non-zero, right? I'm telling you any one which is maximum is going on these axes. If your sigma 1 and sigma 2 is 0, then sigma 3 is non-zero, right? Then maybe sigma 3 is going here and sigma 2 has 0 going here. Then you will lie on this axis somewhere. Deepak, making sense? Or should I explain it again? Got it, right? Perfect. Okay, Mira. So can you explain significance of quarter 2 and 4 in the graph which are slants instead of straight lines? I'll explain you that, Mira. So although, please listen to me carefully. Hopefully this will answer your question. This slant height is basically replicating our relation between tau y and sigma y. Now, please listen to me. Your tau y and sigma y has a ratio of 0.5. Correct? If from the principal axis at an angle of 45 degrees, you draw a perpendicular to this line, this length segment shows you that ratio. Mira, if you recall, the relation between principal stresses and maximum shear stresses is 45 degrees, right? Do you agree? Mira, if you recall basic elasticity, correct, right? That if your principal plane is theta, then your maximum shear stress plane is theta plus 45 degrees. Correct? And now, magnitude wise, if your principal stress is this much, what is your shear stress? It is half, right? That's what your relation is saying. If your principal stresses are something, then your shear stress is half of it. So this slant height distance is actually controlled by what is the relation between sigma y and tau y, which is in our case, tau y by sigma y is 0.5. I will showcase this in a more detailed way when we go to next theory. You will find it more interesting there. But I hope I have given you some insight about your question. Is it making sense? Perfect. Okay. Sir, I've seen shear diagonal in these envelopes. Can you explain it? What do you mean by shear diagonal? We don't need anything apart from the envelope, outside envelope. Inside it, we are not going to draw anything, and it is not required also for theory, for designing our structures. Yeah. As far as you are inside the envelope, you are safe. All right. There, things will get more interesting when we move forward, and this is the next theory. Listen to it, understand it properly. 99.9% of your gate numericals are on this theory. And the reason is 100% of your gate, not gate, 100% of your aircraft components are designed with this theory. Up till now, in all my industry experience, whatever work I'm doing up till now, I have never used any theory apart from one missus. The other theories are based because, frankly speaking, I have never worked on brittle components. I worked only on ductile, and this is the most widely used theory for designing any aircraft component. And the most important name you should remember is von Mises. Any software, ANSYS, Abacus, OptiStruct, Nastran, any software Once you do any analysis, they will directly tell you what are von Mises stresses, and you can directly compare it with the materials, and directly it will tell you there is a failure or a pass, and you will directly take that report to your product designer or developer or anyone who's designing or the product owner, and you will tell this is a failure. Then they will ask you to change the design and blah blah. This you will do your entire life. Now, this theory has some interesting names. Another very common name, I'm coming to that. I will explain this completely. That was your 2024 question, Punesh. Let me finish this, then we will come to all the doubts of them. So, von Mises theory, another most common name given to it is distortion energy theory. All right, so they can use anyone in your GATE exams. Up till now, they have always used von Mises, but people know this as distortion energy theory also. Although it is very limited in standard textbooks, this theory is also known as octahedral theory. But believe me, they can never ask this in your GATE exam. Another name to it is shear strain energy theory, Mrs. Hankey theory. These are some uncommon names. So, frankly speaking, I don't want to complicate this and I don't want to leave anything also. But please remember this name and remember this thing. All right. Next point. So, we know the name. Next point. This theory is also applicable to ductile materials. This doesn't mean you cannot use this theory for brittle materials. You can, but it will give you wrong answers. But it gives you best answers when you talk about ductile materials. So you have two theories for ductile materials now. First, we have learned is Tresca, which is also known as maximum shear stress theory. And second is von Mises theory, which is also known as distortion energy theory. All right. Very simple statement. First of all, what is this distortion energy? This distortion energy is nothing but a fancy name of shear strain energy. But the problem is, we have not learned any kind of strain energy like this. What we have learned is strain energy in bending, strain energy in torsion, strain energy in axial loads. And if you people recall, we have learned something like this. M square dx divided by 2 EI. In torsion, strain energy was T square dx divided by 2 GJ. In axial loads, you have learned it is P squared dx divided by 2 AE and so on. But we have not learned anything like shear strain energy. And that too. So this is the formula I want you people to remember. Even any textbook has not gone into this. This is, if you really want to go into this derivation, we need to open some journal papers because this is already being defined by von Mises. The two scientists has already defined or derived this expression. But what is important for us is if your system distortion energy, which is given using this formula, please listen to me. There will be slight confusions here and there. I will try to explain it as far as possible. And hopefully, I will give you some derivations also here. But again, I will block everything which you will learn and revise for your GATE exam. So, distortion energy is basically given as this sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. If you know I told you any theory of failure will work only with principal stresses. So if you know your principal stresses, you can apply Tresca. If you know your principal stresses, you can apply von Mises. But for that, the expression which you are seeing here is known as distortion energy. This is the energy required for any system to change its shape. All right. If your energy in the system is less than equals to the material maximum deformation energy, then you have a safe material. Keep this in mind. Theory of failures are simple things. Everyone has different criteria. Tresca was saying if your maximum shear stress is less than the material maximum shear stress, you are safe. One miss is saying don't look into shear stresses. If your distortion energy is less than the material distortion energy required, you are safe. Otherwise, there is a failure. But now comes the problem. No one will give you this in your gate exam or not in gate exam. No one will give you this in your company also. If you start working let's say you're working in Airbus, right? They will directly tell you sigma y for material, maybe tau y for material. No one will bother to give you UMAX. They are not theoretical people, right? They are, I can say, they're working in the physical world. So there's simply no material properties as sigma y, tau y, that's it. But one Mrs. has given this expression. So what people thought, let's do a tension experiment again. Now, everyone knows what is tension test. You take a specimen, apply sigma y to it. Sigma y is normal stresses for which the material fails. And in these cases, my sigma 1 is tau sigma y, sigma 2 is 0, sigma 3 is 0. So guys, I have not done anything fancy. I am doing exactly same test what I did. But now I take these stresses, rather than applying to Tresca, I'll apply these stresses to von Mises. Let's do it. Tell me what you will get. So you have 1 plus nu divided by 6c. Sigma 2 is 0, sigma 3 is 0. So this is 0, this is 0, this is 0, this is 0. So if you people agree, you will get this as 2 sigma y square. And beautifully, we will got this as, if you people agree, we get this as maximum strain energy, right? Maximum shear strain energy. So what I have done, I have taken these values. I have applied in this equation. I got this expression. So tensile test has given us an important expression for distortion energy. Now, if you take this distortion energy and substitute it here, you can see this 1 plus nu by sigma E will got cancelled out. I'm not cancelling it here. And the final expression which you're going to get will look something like this. Sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. If it is less than equals to 2 sigma y square, we have a safe material. Now, why this derivation is being done? This is done so that we have a thing which is usually given to us. No one will come and say distortion. Even if you talk to industry people, right, and you say the word distortion energy, please tell me the formula. No one even bother about it. But everyone knows what is sigma y because this is how the catalog comes. Different suppliers will tell. We have done so many numericals, right? Sigma y from material X, material Y, material Z. That's what you will be doing throughout your designing phase of any component. So we have reduced this difficult expression into a more meaningful expression which you can use in your gate exams. So I end up with this formula. So I will not be using this for solving numericals, but they can ask this in your exam, which one of them is the correct option for one misses. So you at least you should know this in your notes, but all the numericals will come here. But if you see, this is for a 3D body, right? What if I have a 2D body? Many things you solve in 2D in aircrafts. So for 2D, sigma 3 will be 0, right? Just do it in 1 or 2 steps and you will be clear. I'll make this sigma 3 as 0. and I'll open the brackets. Sigma 1 minus sigma 2 whole square. So this becomes sigma 1 square plus sigma 2 square minus 2 sigma 1 sigma 2. And then you have sigma 2 square and sigma 1 square. So plus sigma 2 square plus sigma 1 square. And on this side, you have 2 sigma y square for a 2D body. If you clearly observe twice, twice, and twice, I can take 2 common and this 2 got cancelled out. So von Mises theory for a 2D body and all of your gate numericals. Guys, when I'm saying all 100% of your gate numericals, and I can guarantee you 2026 numerical also will be on 2D, your equation is reduced to sigma 1 square plus sigma 2 square minus sigma 1 sigma 2. If this expression is less than sigma y square, as per von Mises, we are safe. If your left hand side is more than sigma y square, then your system will fail. So what expressions you should buy hard? This expression, very general, never asked in aerospace. They have once asked in mechanical paper. Second, for 3D, the equation looks something like this. Now, I have seen people, I have framed some test questions also on this concept. What people do is they forgot this 2. And even if they remember this 2, they will put this 2 here and you will get 0 in your exams. I'm saying only in learning formulas. So when you're learning for 3D, you have all sigma 1, sigma 2, sigma 3, and you have 2 here. When you go for 2D, this 2 got cancelled out and this is your final expression. I star mark this. I told you all of your gate numericals till date are on this theory. Not only aerospace, even mechanical and civil has always gone to this formula only. Now let's discuss your doubts up till this point. Then I'll move forward. Tell me, guys, whatever question you have. If it is clear, give me a thumbs up. Then we'll move ahead. Clear? Now, before going into further topics, please listen to me carefully. Let me do this in Tresca also. Guys, I have given this explanation many times, but let me repeat this part again. You know that it is never good to design our material for yield because at this the system will fail, right? Correct? At if your stresses reach yield stresses, system will 100% fail. And as an aircraft person, we never do that. We always keep some factor of safety. Vishal asked this, so I'm explaining this point. So let's say if your yield stress is 200, all right, let's say there is some yield stress of 200 MPa. And if you design your system with this, you are saying that you should keep your stresses less than 200. If it is 199, you are good. If it is 200, you are at the border. Still, it is good, but you are at the border. 201, your system will fail. 100% your system will fail. This is a very dangerous system because you are designing your system till 200, right? So what people say in aircraft, don't design these things for yield stresses. What you do is factor of safety, which is denoted as N, is nothing but your yield stress divided by your design stress. Meaning, we will not going to design anything for yield. We will going to design it for some other value. For example, if your factor of safety is 2, and your yield stress was 200, then what is your designing stress? Your designing stress is 200 divided by 2, right? If you people agree, can I say my designing stress is basically yield stress divided by n? Or it can be any yield stress. Now, I have explained you completely that if your stresses are less than equals to shear stresses, then your system is pass. From now on, what we're going to do is, if factor of safety is provided, we will not going to compare our stresses with yield stresses. What we're going to do is this max of any one, whatever maximum shear stress you have, take that value. And if they ask, you should design your system for this stress. This becomes more generic formula. If factor of safety is 1, that means you're not bothering anything. You're designing for yield stresses only. Exactly similar way, if you have factor of safety given, it should be sigma y by n whole square. And here also, it should be sigma y by n whole square. So what you're doing is you're not designing your body for just the boundary. What if you designed it? You say for these stresses, the weight on the aircraft should be, let's say, 1000 kg. But there are people who are stealing things, right? During the airport security check, you keep extra luggage in your laptop bag. You some keep some extra luggage. You are allowed 20 kg and you take 21, and the person who is checking also says it's okay. Then you are in very danger, right? You said 1000 kg. People are doing these things. So maybe during the flight your weight is 1050. Then if you design directly at yield, your system will fail. So to keep those things into account, some bad things happening maybe during the applications, you keep factor of safety. So you design your system with a factor of safety of n. Let's learn this expression. If nothing is given, take n as 1 and it becomes your generalized expression, what we have seen. So similarly, sigma y by n whole square, and similarly here also tau y by n. And if you want, you can convert that into sigma y by 2 and so on. I hope this factor of safety thing is clear to every one of you. Now, so we have the formula, we have the name. Now comes what is the ratio. Now, again, we can perform a torsion test, but again, one misses, all these people have already done that. The relation, if you apply a torsion test, the relation between tau y by sigma y is basically 1 divided by root 3. Now, if you convert this 1 divided by root 3, you will get this as 0.57. If you see the ratio for Tresca, tau y by sigma y was 0.5. Now, what this equation indicates, please listen to this. Okay, let me come to this diagram in a bit. I'll remove this. And please keep this in mind. I'm talking about one misses. So I have my two stresses. Sigma y is definitely a criteria for me. So what I'm going to do is I'm going to take some points, sigma y, sigma y, sigma y, and sigma y. All right. And now, please listen to this. I have explained this concept before, but let me explain that again. If you see this theory, right? This theory has squares in it. See, sigma y square. Here, stresses are also in square. If you see in 2D, you can clearly observe stresses are in square. It's an energy-based theory. Energy is stress square. Strain energy was m square divided by 2ei. Correct, right? Square terms are not straight lines. Square terms are curved lines, kind of a parabolic curves, right? So what I'm going to do is I'm going to join these extra points with curves. And what you're going to get will be the graph for von Mises theory. Now, and you will feel good. Let me finish this explanation. Believe me, I think after 5 minutes, you will be okay and good with this. And Mira, I hope this will answer your question now even better. If from now at an angle of 45, you try to convert your sigma y into tau y, this ratio will be 0.577. This was zero point 0.5 for Tresca. This is 0.57 for von Mises. Now, there is a chance that still people have some doubt. Let me explain that. And hopefully, this should address your concern. Purnesh, you asked me this, so this will answer this. The best way is I have taken a plot in which you have both the theories together. So this is your sigma y, sigma y, sigma y, sigma y. And now what we will do is we will draw Tresca. So I will join these ends with straight lines. So if you are inside this Tresca, you see I have already shown it here. Tresca, which is maximum shear stress theory. If you are inside this zone, you have a safe design. Everyone is absolutely clear in this. Von Mises came and say, don't do this. You cannot look into shear stresses. If you want to design your system properly, you should look into distortion energy. And then he proposed altogether a different theory. And with that theory, when we draw the diagram and when we saw, because it is energy based, I have taken these points and now joined these points with curved lines, not straight lines. And what is the reason? All there were square terms. If you join them, you end up with this graph. That means, according to von Mises, if you are inside this envelope, you are safe. Guys, please listen to me. I'm answering your 2024 gate question now. Please listen to me very carefully. So Tresca says, if you are inside the black body, you are safe. Von Mises says, if you are inside the red body, you are safe. Can you people tell me if you are here at green point, is it safe for both people, or is it safe only for Tresca, or is it safe only for von Mises? Green point is safe for what theory? So both people will come and say you are good, design it, no problem. Perfect. Tell me if you are here. What you people expect both theories are telling you. Both are predicting failure. So both are saying if you design this body, you are going to fail 100%. Now, I hope you already got my answers. If you are here, let me take some bright color. If you are here, 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 can you people tell me who will say it passes? It is safe for von Mises, but it fails in Tresca. Correct? Everyone agrees on this? Now here comes the thing. As a designer, whom you will listen? Will you listen Tresca? If you are standing here, if you are standing here, Tresca is telling you if you fly with this aircraft, you will fail. One Mrs. is telling you if you fly with this aircraft, it's okay. You are working fine. Now, what this tells us is this. Tresca is more conservative theory. Now, conservative means it doesn't allow you to do much things. If it try to put you in a more constrained position. Now, what do you mean by this? You did some analysis. You are designing your wing, let's say, and Trisca came and say that if your thickness of the wing is more than 2 mm, if your thickness is more than 2 mm, your system will going to fail. Trisca is telling us this. Von Mises, which is slightly relaxed theory, you can see it gives you some buffer also, right? We'll say even if you go till 2.5, right? It's okay. After that, only failure will happen. So Trisca is not allowing you to go to higher terms. No, no, no. My bad. Guys. Please discard this. I have given you wrong statement in terms of this. Please listen to me. I'm explaining that point again. Trisca says you can use thickness of 2 mm for a safer design. Of any component. If you use thickness of 1.9, your system will break into pieces. Von Mises, on the other hand, comes and says you can even use 1.55. You are having a safer design. You know, when you have less thickness, you will have more stresses. When you have high thickness, you will have less stresses. That's what Trisca is restricting you. Trisca is restricting you to lesser stresses. Lesser stresses means Trisca is conservative and Trisca gives heavy designs. Why? Trisca is saying use 2 mm, otherwise you will fail. One Mrs. comes and says, why you are wasting so much of amount of material? Just use 1.5, you are good, you are safe, don't worry about it. So automatically, Trisca gives you heavy designs. It is overprotective. Yes, you can use this word overprotective. We use this word in for our parents, right? Overprotective, protective, conservative parents, something like this. But they are just trying to protect us. Correct, right? Exactly same way. Trisca is overprotective, but in the process, it gives you heavy design, and Trisca gives costly designs. Why costly? More material, more cost. Now you tell me, as an engineer for aircraft applications, let's say which mud theory this was asked during my interview, during my campus interview in IIT Kharagpur. This was the question asked, guys, which theory you will use to design, and they have given me a particular component. Can you people tell me, for an aircraft designer, which theory you people will apply? Keep one thing in mind, Trisca is always safe. So Priyal says Trisca, Akash says depends on component, Priyanka says one misses. All right, so keep one thing in mind. Even we are using one misses, people feel it is not safe. But with one misses, we can have factor of safety, right? So it's not like we are not having safety with one misses, but one misses gives you lighter designs, much cheaper. And typically for all aircraft applications, we always go with one misses. But strictly speaking, if you, let's say you want to design a bridge, a railway bridge. In railway bridge, first of all, weight doesn't matter. This thing doesn't matter, right? Second, cost doesn't matter because it is one time investment. The bridge will have a life of maybe 20, 30, 50, 100 years. So we will design those things with Tresca. We will be overprotective. But when it comes to aircraft, we have a limited time period or limited life of an aircraft. Second, aircraft always go under maintenance also, right? Every time it lands, there is a maintenance, there are regular checks. So you are always safe. And anyhow, we are using safer factor of safety for one misses also, right? So guys, please keep this in mind. Typically in aircraft, always one misses is being used as an application. Now, before opening for doubts, let me show you what we have done so that it gives you confidence. We will solve all these numericals. Please don't worry about any of this. This is the question asked in 2024. Question number 46. So this is asked for 2 marks. Can you please read this with me and tell me? The figure shows plots of two of loci of an isotropic material where sigma 1, sigma 2 are principal stresses, sigma y is yield stress. Which of the following statement is or are correct? So this is a multiple select question. I'll give you maybe a minute and so think about this. This is for 2 marks. What you people feel is the correct option. And now you can understand why I am stressing on these theory points, why I am giving you so many examples so that you people are comfortable with anything which comes in your exam. Already many people have given me the answers. So criteria P, you see is a circular thing, right? So circular thing means one misses. Criteria P represents one misses. Absolutely true. Priyanka, there is not only one answer, it's multiple select, right? Criteria Q is for Trisca. Perfectly correct. We have just now seen this. Criteria P represents Trisca. Wrong, wrong. So A and B and C this guys, this is asked for 2 marks in your GATE exam as multiple select. Are we clear? Are we good in this? Have we understood these concepts? Are we together? Any questions? Please ask me. I will repeat it again. Okay. I have a doubt. Then, if due to cabin pressurization or even a hard landing, the structure fails, so isn't good idea to consider Trisca. That's what I'm saying. You're already carrying heavy weight with Trisca. Why to consider that? We have factor of safety with us, right, Priyal? If you have a, let's say, landing gear, have a factor of safety of 2, 3, maybe more. But there is no point of going in Tresca and having a heavier design, right? And you can go. I'm not denying that you cannot go. You can propose, but company will take only if one miss is giving you a lighter weight. Company will always go with that. I don't think any other doubt. Okay, let's move forward then. So then our third theory is what is known as maximum principal stress theory. Is there two statement that factor of safety is overriding factor over weight penalty? Weight is increasing, right? With factor of safety, Akash. This is the reason for aircraft we typically use 1.2 and 1.3 factor of safety. We don't go for 2, 3, 4. Even for automobiles and all, you can go even with 3 or 4 factor of safety. With bridges and all, you can go to 20 also. With buildings, you go for 20. But for aircraft, you go with 1.2, 1.3. More the factor of safety, more the weight of the design. All right. Next, principal stress theory. Now, this is the easiest theory. Maximum principal stress theory given by Rankine. So, Rankine theory or maximum principal stress theory, both the names you should know, you should remember. And now, from now on, all the three theories which are remaining are used for brittle materials. But you can use them for ductile, but they will give you wrong answers. They can give you some wrong interpretation. Maybe it will say it's a pass, but ductile material is actually a failure. Or sometime it can give you heavy materials, heavy systems. So it is not advisable to use these theories for ductile materials. Ductile only two theories, Tresca and von Mises. Now, as the name suggests, maximum principal stress theory. How many principal stresses we have? We have sigma 1, sigma 2, sigma 3. Take the biggest of them all. And if your stress is less than equals to the material ultimate stress, it's a pass. If your material is having, if your system is having more stresses than the ultimate stress, it's a fail. Now, one important caution note. In some books, maybe you will find this as sigma y. Don't worry. Whatever maximum stress is given in the numerical, we will use that to solve the numerical. I told you this can be applied for ductile also. Ductile fails for yield, brittle fails for ultimate. If you apply it for ductile, you can find sigma y in your expressions. So this is very simple formula. No maximum shear stress, no distortion energy, simply comparing our principal stresses. Ratios. Tau y or tau u in this case, with sigma u is equals to 1. So absolutely no difference. Whether you have, because it's a brittle material, in any direction you pull, it simply ruptures. And diagram for this is a square. Let me write it. And it looks something like this. So again, we go to points and we join them. So this simply says if your stresses are within this zone, and guys, you can even check this. If you calculate this distance, right, it will come out to be 1. So this was 0.5 for hexagon. I should not complicate this, but I'll remove this part, but I will draw this now. This was Tresca. Correct? And this was 0.5. Now you have this ratio as 1. Don't forget these are nothing but your stresses. And you have plus ultimate stress, minus ultimate stress, plus ultimate, minus ultimate. Anywhere you are inside this zone, as per Rankine, you have a safer design. Anything outside, you have a design which will fail. Now, the only drawback of this is never asked, but I really feel if they really want to complicate things in the exam, right, they should ask these things. But interview people will not leave these concepts. They will ask you these questions. The problem with maximum principal stress theory is that it takes tensile and compressive strength as same. Now, understand this. If you see, they are saying in tensile direction, your ultimate stress is sigma u. In compression direction, that means you have negative stresses, your stress is still same with negative. But you people know in reality, if I'll give you a bar made up of any material, and if you pull it, it fails. But if you compress it, believe me, guys, it is maybe 10 times or 100% times more difficult to break this body. Crushing, I told you, is really next to impossible. Even if I'll give you a very simple, soft material, right? You can break it into two pieces with tensile very easily, but compressive is difficult. This is the only drawback, that it takes both tensile and compressive strength as same. And this is only a note just for your knowledge, not for your gate. To overcome this drawback, there is a theory which is known as Mohr circle theory of failure. This is basically the sixth theory. You will not find this in every textbook. Most recent theories, recent new textbooks, or some international author books, you will find this. But you will study this theory in your, as I told you, advanced elasticity in your IIT first semester course. This is the theory with which overcomes this drawback. And it will actually takes into account that a body will fail easily in tense tension in comparison to compression bodies. So we have our third theory, we have the name, we have the equation, we have the ratio, we have the graph, and we know when this theory should be applied. Give me a quick thumbs up if it is okay, fine for all of you. If yes, then we'll move to the next body. The next two theories which we're going to discuss is never asked in aerospace. I have not seen in mechanical in last maybe 10 years. Even I have not seen this in IES exams also. But still, we should have it because these are five standard textbook theories. Anytime they can ask in your exam, we cannot rely on those 2 points. So the fourth theory, what we have, is known as maximum strain energy theory. Now keep this in mind. Second one was maximum shear strain energy, which is also known as distortion. So there is a difference. But as the name suggests, it's an energy based theory, guys. Energy means square terms. Square means graph will not be straight lines. It will be kind of curves, parabolas, kind of things. So name is maximum strain energy theory. It is given by Haigh. So it is also known as Haigh's theory, and it is used for brittle materials. All right. Now, this theory equation for 3D looks something like this. Please remember this expression. If they ask, they cannot frame a numerical on this, but they can ask, match the following. And so I will show you the gate numericals. You will understand this. So for a 3D, the easiest way to remember this is this: sigma 1 plus sigma 2 plus sigma 3 whole square. I told you energy theory is square based, minus 2 into 1 plus nu sigma 1 into sigma 2 plus sigma 2 into sigma 3 plus sigma 3 into sigma 1. If all of this expression, which is known as strain energy, there is a derivation given for the strain energy in Timoshenko and Gere only, not in Megson, not in strength of material books, but you will find this in Timoshenko and Gere. And if this is less than equals to sigma y square, you have your Higgs theory defined. Now keep this in mind. This is for 3D body. There is another way of looking into this. What you can do is, I'm not doing it now, but what you can do is you can apply a plus b plus c whole square formula. You can multiply this inside, and same expression can also be written as this. You can learn any one expression, whichever you feel you are comfortable with. You will get this expression as this. I'm again telling you, this is same expression, just applying some maths trigonometric formulas. Any one formula, or at least both, take a picture in your mind and keep it. If in the exam it is match the following, you can mark it. They have not even gone into 3D for one misses, and all the gate numericals are on one misses up till now. There is only one theory question on Rankin theory, that is theory number 3, maximum principal stress theory. For 2D, you can simply make sigma 3, sigma 3, sigma 3, 0. So you end up with this expression, sigma 1 square plus sigma 2 square minus 2 nu sigma 1 sigma 2 less than equals to sigma y square. This is more relevant theory, or a question can be asked. They have never done that. If it is not done in mechanical, it will 100% not will come. It will not come in aerospace also. But please, I have seen people doing this mistake. This is very similar to how one misses looks. Sigma 1 square, sigma 2 square, minus sigma 1, sigma 2, and sigma y square. Here you have an additional term, which is 2 nu. So when you're learning, please don't forget this term. I don't want you people to lose your marks. Now, ratio. Sigma y, sorry, tau y by sigma y here. If you see, this theory needs Poisson's ratio of the material. Von Mises don't bother about Poisson's ratio. Tresca didn't bother about Poisson's ratio. Rankin didn't bother about Poisson's ratio. But Haig's theory bothers about Poisson's ratio. So this ratio, tau y by sigma y, is not a fixed value. It actually depends upon the material. Now, just to give you a feel, if let's say nu is 0.25, typically for aluminium steel, it is 0.28, let's say roughly 0.25. If you substitute this 0.25 here, it becomes 1.25, that is 2.5, 1 divided by 2.5. I think you will get this as 0.4, just to give you a feel. It's an energy based square terms. Ratio is giving you 0.4. So graph, oh, there will be a root here. Okay, maybe, sorry, maybe I have missed it. I don't have the formula with me. Sorry. Can you tell me you are getting 0.4 with under root or without an under root? There is a square root, right? So graph will be very much similar to one misses. It will be something like this. But now, from this center point, if you drop a perpendicular, this will be 0.4. So you can see, although you cannot compare one misses with Higgs, you cannot do that because one is for brittle materials, one is for ductile. But just to get a feel, it's this envelope is slightly lesser compared to von Mises, and this is what is known as Higgs theory. Open up, guys. If it is fine, give me a thumbs up. We'll move to our last theory. Perfect. Great. Fifth theory is what is known as maximum principal strain theory. This is given by Saint Venant. So Saint Venant's theory applied for brittle materials. Now this is self-explanatory. Maximum principal strain. Now, if you people have done basic elasticity with me, right? You know how to apply Hooke's law. So if you want to calculate strain in any direction, this is just for a revision. Stress in that direction will give you a direct effect. The other direction will give you a Poisson's effect. And the other direction will give you a Poisson's effect. Please give me a quick thumbs up. Do you recall writing these kind of equations in Hooke's law? Correct, right? Now, we are talking about principal strain. So I will be using my principal stress in one direction. Then my other principal stress will give me this. My third principal stress will give me this. And if my strain, principal strain, is less than the material maximum strain, then I have a I have a pass. My material is good. Now, what is this? Again, you people can do a tensile test. In tensile test, your sigma 1 was sigma y, sigma 2 is 0, sigma 3 is 0. Correct? You don't have to do any of this in your GATE exam or even for revising. If you put sigma y here, sigma 2 as 0, sigma 3 as 0, you will get your strain as sigma y by E. And then I'll substitute it here. Maybe I'm going a bit fast, but I'm assuming that I'm repeating this again and again. So if you substitute this sigma y by E in place of strain, E and E got cancelled out. And the expression which you will find in books is something like this. Sigma 1 minus nu into sigma 2 minus nu into sigma 3 less than equals to sigma y. That's it. So rather than comparing strains, we have done a tension test, got a simple relation, and get an equation which we will learn. If you see, I have not blocked this equation. This is only for your understanding. Maximum principal strain energy theory, not energy, maximum principal strain theory or Saint-Venant theory equation looks something like this. Then again, we have to convert it, right? And if you see, this theory is also dependent upon nu. This is again dependent upon mu, right? So tau y divided by sigma y is something like this. Again, just to get a feel, if nu is 0.25, you will get this ratio as 0.8. So graph for this body is kind of a rhombus. Let me write that word here. So graph for this is a rhombus. And it will look something like this. As I told you, these theories are not directly applicable for ductile materials, but if they ask, I will do some practice questions with you in which I will ask to apply this theory for ductile material. I will ask von Mises to apply in ductile, and we will practice many questions. I have more than 10 additional questions apart from GATE to practice. But this is all I have for all the 5 theories, in which 2 are applied to ductile and 3 were applied to overall summary. Hopefully, this will conclude our lecture. If you see first theory which we have studied, Maximum shear stress theory. This was Tresca. I will mark this in red. Tresca, it was not an energy based, so it should be straight lines. And if you recall, it was a hexagon. So theory, if you see, it's here. Very conservative theory. Second, we have seen is von Mises, which is maximum distortion energy theory. Now, this is energy based, so it was having some square terms. So theory was this. And you know the distances also. Red line will have 0.5, green line will have 0.57. Third, what we have seen was maximum principal stress theory. This was nothing but Rankin, right? And this was simply a square. And the ratio was 1. Then, fourth, it is not mentioned here. It is Haig's theory, but hopefully you people can understand this theory will be something like this. It is a parabola with a ratio of 0.4. And the last theory which we have seen is maximum principal strain theory. What was the name of the scientist? Saint Venant. Saint Venant. And this is kind of a rhombus. And the distance is 0.8 or something, depending upon new. You cannot learn 0.8. Any new value will change this expression. So this is the overall summary. Although this is not good idea to compare these two theories with the other two because these two are good for ductile materials, whereas all remaining three are good only for brittle materials. Tell me, guys, are we okay in theory of failures and we understood all the five theories? Tell me, guys, please.